let's recall Morera's theorem, because some of the things we do today are consequences of Morera's theorem. So you have a D, an open disk, and you have F, a continuous function on that disk. And there's a condition for holomorphicity, right? That if for every triangle T contained inside of D, you have that the integral over the boundary of F is 0, then you know that F is holomorphic. Okay, so that just to remind you what Morera's theorem says. Okay, so we'll use Morera's theorem to show that various functions are holomorphic. And the first thing we're going to do is what Stein calls holomorphic functions defined as integrals. Okay, so the setting is that you have omega, an open set in the complex plane, and you have a function that's on omega cross 0, 1, right? So you have the Cartesian product, right? You have some omega, right, and then you cross it against 0, 1, and you get this sort of object, right? And so here's your omega, right? Here's your interval I, right? And you take the Cartesian product of them. Okay, and so the claim is that if F is continuous on the Cartesian product, and further, for each S, S is holomorphic. So right, each of these S's is at a different height, right? And what you're saying is that F is going to be holomorphic, considered as a function on omega at that height, right? So F dot S, of course, is a function from omega. I mean, each of those is a function from omega to C, right? So if each of those slices is holomorphic, then when you define f of z as the integral from 0 to 1 of f of zs ds, then that is also holomorphic. Okay. So, right. So the way you want to think about this is that this is an average, right? This is really an average, right? You're taking the integral of this function, right? You're taking the integral of this function over this interval, and then you're dividing by the length of the interval, right? So this is an average. This is an average value, right? For each z, right? For each z and omega, you're integrating the function over that interval, right? And that gives you an average value over that thing. So what this is saying is that this sort of average of holomorphic functions is still going to be holomorphic. Okay. Okay. So the proof of this is there's Stein remarks about two possible proofs. So he says, well, let's take let T be any triangle in omega, then it would be good enough if we could show that the integral over every triangle is 0, right? So it suffices to show that the integral over every triangle is going to be 0. Right? He says, well, one way we can do this is to say, well, when we're integrating this function over the triangle, right, we get this integral from 0 to 1 of this thing, right? So d dz. Right, so you want to show this sort of thing. So one thing that would be nice would be if you could change the order, right? If you could change the order of integration, right? Then you just say, well, look, FCS dz ds, right? And then we know that each of these guys is holomorphic, right? Each of these guys is holomorphic, so each of these things is 0, and we get 0. Okay. So if we could change the order of integration, we'd be done immediately. To do so requires using so-called Fubini's theorem. I think maybe Stein didn't want to go through the hassle of proving Fubini's theorem. So instead he gives a more direct approach, and an approach that's going to be useful to us when we prove Runge's theorem later on. So says, well, instead of going that way, let's take a different route and say, let's take Riemann sums. So let f sub n be the sum of the values at times k over n as k ranges from 1 to n, and then divide by n. Okay, so right, you've got your object, right, and you're saying, okay, we're going to divide the interval into n parts. We're going to sample the function, right, at each z. We're going to sample it at those n heights, right? We just take those values, we add them together, and then we divide by n. So we're taking an average, right? And in the limit, that's going to tend towards your integral, right? Okay, so this is the sort of like discrete average of f at heights 0, 1 over n, 2 over n. Should be, I'm sorry, at heights 1 over n, 2 over n, up to n over n. Okay, and so notice that, well, so you're just taking the functions at these along these different slices. You're adding together, and then you're taking the average, right? And so each of these is holomorphic. Each of these guys is holomorphic, right? Because each of these guys is holomorphic. You're just taking a finite average of holomorphic functions, right? Okay, right. So what we want to show. We want to show that the f sub n converge uniformly to f, right? Because if they converge uniformly, then we can change the order of integration. We can change integration with limit, right? So if we do, for then the integral of the limit is going to be the limit of the integrals, right? Well, the limit is going to be f, right? And then the limit of each of these integrals is going to be 0, right? Because each of these guys is holomorphic, right? So when you integrate them, you get 0, right? And so if we can show that we have uniform convergence, then we're done. Okay? That by Morera's theorem, that gives this to us. So. Okay, so we need to show uniform continuity. Uniform convergence, and what we'll use is uniform continuity. So, fix an epsilon, by uniform continuity. by uniform continuity, we know that there exists a delta such that if the distance between S and T is smaller than delta, then the distance between f of zs and f of zt is smaller than epsilon. Right. Right, because we have uniform continuity of f on the disk cross 0, 1. Right. We can take like the solid disk. Right, with the closed disk cross 0, 1, that's compact. Right, so we've got a continuous function on a compact set. So we've got uniform continuity. Okay. Okay. Okay, so, okay, yeah, no.
Is the disk here like something we've defined before, or is this just like, given a point z, we just like define some disk around z which is contained in omega?
Sorry, maybe I probably didn't make it clear enough. So when we're going to show holomorphicity by Morera's theorem. So that is, given any disk, we'll take a disk and we'll take triangles within that disk. Okay, and then we'll show that the integrals over the triangles within that disk are always 0.
Okay.
So the disk is the disk that contains the triangles.
Okay.
So I didn't write it. So yeah, thank you. Is that okay?
Yeah.
Yeah. I didn't explain what it was. Okay. Okay. I should also say that if I'm going like this, it's because I had something called a vitreous detachment in both of my eyes a couple years ago. So that's when the vitreous humor in your eye pulls away from the back of your eye and might even rip off your retina with it. And so they had to laser like my eyes back together, sort of. And so I don't see that well. And so like if I'm going like this, it's because I'm trying to see more clearly. Yeah, so when you get older, things to look forward to. No, it's because I've got such poor vision. The people with poor vision are more likely to have this happen. Okay. Yeah. Yeah. It was actually kind of interesting because for weeks afterwards, I could actually see the after image of the vein network on the back of my eye, like overlaid over everything. Yeah. Yeah. Okay, so yeah, just to explain why I may look like I can't see you, it's because I can't see you. I can see you, I just can't see you perfectly clearly anymore, right? Like, yeah, I can still drive. Okay. Okay, so we're trying to show uniform convergence, right? So we need to look at this sort of thing, right? So for right, we need to look at this sort of thing for z in the disk. Okay, so right. So what is this? Well, this is right. This by definition is just going to be the yeah. Let me write it like this. Okay. So yeah. Let me do it slowly so I don't get lost here. Right. We've got this guy, right, and then we're subtracting off. This guy. Well, this guy is the integral from 0 to 1 of f of z s ds, right? Of course, that's just by definition, right? And we're going to rewrite this guy. We're going to rewrite this whole thing as follows. we're going to write it as the integral, as the sum from k equals 1 to n of the integral over k minus 1 over n to k over n, right? Right, so we rewrite this first term like this. Does that make sense? What we're doing is we're just taking a constant, for each k, we're taking, we're taking the value at this point, and then we're integrating over the layer of thickness 1 over n, right? And so, right, that gives us this is just going to be a constant times 1 over n, right? This constant times 1 over n. So I'm just taking this thing and then rewriting this term as this integral. Okay, right? Because we're just taking a constant integrated over that layer. Okay, so right, and then this thing we're going to do the same, doing something similar. We're just going to break it up. Right, so we're summing over the whole thing here. Right, so we've taken this guy. Well, we've taken this guy and also written it as a sum, right, just over each layer. Okay, and then we combine those things together. Maybe I don't need to spell it out so much. So we get the integral, we get these sums of the integral k minus 1 over n, k over n, f of z k minus n, minus f of z s ds. So that's equal right now. Okay, I just combine the integrals together. Okay, but I'm going to so this is equal to this. This is less than or equal to this. Great. Okay. So it's less than or equal to that, and so now take n, capital N, such that if n, little n is bigger than capital N, then 1 over n is less than the delta that we got from uniform continuity. Okay, less than the delta we get from uniform continuity. And so, look, this, on the interval k minus 1, right, k minus 1 over n, k sub n, k over n, right, the distance between k over n and s, right, is smaller than 1 over n. Right? So, right, because s is inside here, right? And the width of this interval is 1 over n, right? So the distance between s and k over n is, one of the endpoints is going to be less than 1 over n, right? Which is less than delta, which tells us that this thing is less than epsilon, right? So we've got an epsilon. We're integrating it over this thing, so we get epsilon over n. There are n of them, so we get n epsilons over n. We get epsilon, right? So we get that this whole thing, then let's call this term star, right? And star is less than epsilon. Okay. So that does it for you, right? You've got uniform convergence, right? You've got uniform convergence on the disk, and so for every triangle, you can change the limit and integration. Is that okay? That's the end of that. Okay. Nice. Hope you like it. Okay. So. I said I wouldn't do Schwitt's reflection, but I prepared it anyway. let's do Runge's theorem first, and if there's time, then we'll go back to Schwartz's reflection. Okay. Okay, so so here's Runge's theorem. Okay. So you have K, compact set in C, and you have yeah, let's do it that way. Okay, and you have omega, an open set, and K is contained inside of omega. So omega is a neighborhood of K. Okay, so here's the claim. Claim has two parts. If F is holomorphic on omega, then there exists a sequence of rational functions f sub n such that, one, the f sub n converge uniformly to f on K, and two, the f sub n have no singularities on K. Okay. So all the singularities are off of K. And then part two, if further K complement is connected, then we can take those rational functions to be polynomials. So there exists a sequence of actual polynomials, P sub n, such that P sub n converges to F uniformly on K. Okay. And of course, there are no singularities anywhere. Okay. So, so the proof relies on a few lemmas, and lemmas are pretty straightforward, I think. So the first goes like this, right? You have a function on some open set omega, and F is holomorphic. If K contained in omega is compact, then there exist segments, gamma 1 to gamma n, contained in the complement of omega, the complement of K in omega, such that for all z in K, f of z equals summation 1 over 2 pi I f zetas zeta minus v to zeta over the intervals, over the segments. Sorry. Okay. So okay, so yeah, you've seen this in the book, right? You have your compact set K, and there's going to be some sort of some sort of collection of segments that go around it that you can integrate over these segments and get the values of f inside. Okay. So. And the process of getting that, those segments is as follows. So let D be smaller than 1 over root 2 times the distance of k from omega. Complement, sorry. Right, so right, you have your compact set. You have your compact set k, right, and you have omega containing it, right, and then you've got some distance to omega complement. You multiply that one. Yes.
Which set is F homomorphic on?
Omega. Okay, so and then you create a lattice on C with side length D. Right. So you right, here's your right. So you create this. You create, basically you lay down, a bunch of squares of side length D. Okay, and let Q be the set of all squares, Q1 through Qm, all the squares, all the closed squares intersecting K. Okay, so here, right, everybody who intersects K. Right, all these guys intersect K. Okay. So the first thing to notice so observe that each of the cubes, each of the squares lies inside of omega, right? Because each of them intersects K, right? And the distance from if they intersected omega complement, that would mean that the distance from K to omega complement was smaller than D, which is, would be smaller than root 2 times D, which would be the distance. So, right, so like, or else the distance from K to omega complement would be smaller than root 2, smaller than the diameter of Qi, which is root 2 times D. Right, which would give us again the distance. So we get contradiction. So each of the Qi is contained in contained in omega. Okay, so now pick any z in K that's not on the boundary. So not on any of the boundaries of the squares. Okay. So we're inside of K, but we're not on the boundary of any of these guys. Okay. So then you say, well, look, we know that Z must lie in some Q sub I. Right? So Z must lie in one of these Q sub I, and so if we by the Cauchy integral formula, we know that 1 over 2 pi I we know that this is going to be f of Z, right? For that particular I, and it's going to be 0 for everybody else, right? And if we take any other, right, and we get this thing, is going to be 0 if k is not equal to I. Right? Because we're not inside there. And that's, so we were integrating a holomorphic function, so we get 0. Okay. Okay. So is that okay? Everybody all right? Any questions? Yeah, go ahead.
So why is the first integral over the boundary of qi not equal to 0?
Because this is our z. Our z lies inside there, right? Right. Our Cauchy integral formula, right? Cauchy integral formula tells us that, you know, when we integrate over some curve, right? This is going to give us f of z for z's that are inside the curve, right? And that's exactly what we're doing here. Okay. So we'll get f of z. Right. The point is that we've got this, you know, this function has a singularity there, right? But, you know, if z is not contained inside, if we're looking at this and z is not contained inside there, well, then we're integrating a holomorphic function, right? So integrating a holomorphic function, we get 0. Yeah, Kyle.
What? So we were picking like a z that's in K but not on any of our boundaries on the lattice. Do we not need to talk about like what if we pick a point that's on the boundary of our lattice? Or
We do.
Okay.
We'll do that in a second.
Gotcha.
Yeah. So yeah. So like case 1. Okay. So what's the point? The point is that, you know, when we integrate the function over any of these cubes, right, in the positive manner, we're either going to get 0 or we're going to get f of z, right? So, you know, if this is our z, you know, we're going to get f of z when we integrate over that guy. We're going to get 0 when we integrate over all these guys, right? So if we integrate over all the q's, right? If we integrate over all the q's, if we add all that stuff together, right? So when we add all that stuff together, boundary of qk as k ranges from 1 to n. That's going to give us f at that point, right? Right, because we got a bunch of zeros, and we also get the value itself. But then you notice that there's a lot of cancellation that goes on, right? So if whenever you have squares that are next to each other, well, you're going to have something that goes one way and then something that goes the other way, right? So notice if squares are adjacent, then we have cancellation. Right. So what we end up with is we end up with summation 1 over 2 pi I we end up with the integral over some interval, over some segments only. Right. So where the the gamma I are the remaining sides, the remaining segments. Right, the ones that don't lie between adjacent squares. Right. In other words, the ones that don't intersect K. The ones that don't intersect K. Right. Whenever you have two cubes and say like let's say K is this object here, right? Then if this edge intersects K, that means that on both sides, right, this edge going one way and this edge going the opposite way, both of those, that it means that both of these cubes are contained in our collection, right? And so that's going to cancel out, right? So the only stuff we have left are going to be the sides that don't intersect K. Does that make sense? Right. The ones that don't intersect K, right? So normally I mock people who use colored chalk, but I wish I had some colored chalk. So you're only going to get these things on the outside, basically. Anyway, just look in your book. There's a better picture. Okay. I hope that's clear. Right? You integrate over all the cubes. A lot of cancellation occurs, and then you're basically left with this stuff on the outside that doesn't intersect K. Yes.
Why bother spreading it up into two cases? Why not just say we can always integrate the outside?
Because you don't have the integral formula, right? You're not going to have the integral formula if your thing is lying on the edge.
Yes, but why can't we just say the outside is a contour for which the integral formula holds? So we can always just integrate around the absolute outside. So take the union of all the squares, look at their boundary, and integrate over that, and do a Cauchy integral formula.
Let me think. So. It's not going to be in K. You know your homework there. Yeah, I don't know. I don't know. That seems like it works to me. But let me, right? Because you've got this curve, right? You say, well, by Cauchy integral formula, this thing is this point is inside there. So
is it just that they're trying not to claim the Cauchy integral formula for this kind of more complex curve, or? Because we only really proved it for circles, but is it maybe that?
I'm not sure. Maybe, yeah, maybe. Yeah, I'm not sure, but yeah, this, I don't see anything wrong with what you're saying.
Okay.
Yeah. Yeah, I was hoping nobody would say this, but, but yeah. Like, why are you doing all this work? It doesn't seem like you need it, but. Okay. Okay, in any case, by whatever, in any case, this is true. This is true. Okay, so, okay, so, that basically does it, except for the case when you're on a boundary, and right.
If you're on the boundary of K, can you just choose an extra square because you have an extra little bit of leeway?
Say it again?
If the boundaries of those gamma I and omega line up and you have a really bad point, can you not just choose an extra square and give yourself a little extra because you chose the squares to be small enough? So then you don't even have to worry about that. So. Or maybe there's something I don't know to do.
So you're saying like, let's, if you are on an edge, then just choose another square,
Yeah,
right?
because you never have to be on the edge unless the boundary of omega and the boundary of some gamma I intersected. You never have to see what f is at that point.
Well, yeah, each of these squares should include their boundary. So if K touches the outside of that square, it should also touch the outside of the square above it.
Yeah,
So we would include that square for the whole contour.
that's true. So you're saying if we're included at all, we're going to be in one of these interior guys, right? We're going to be in one of these interior guys. And so
that covers it.
yeah, if you can use the Cauchy integral formula, yeah. Which, yeah. Okay. Well, the argument that Stein gives is basically that they use continuity, basically that this is a continuous function, and so if you are on a boundary, then you can take a limit of points approaching that point. And so, so by the continuity, the formula is still going to hold. Does that make sense? So like, if Z is on a boundary, then just take a sequence of points for which the formula is valid, and then choose WK that approach Z, and then because the formula is true for all the WK, then in the limit, it's by continuity, it's still going to hold. So. Okay, good. Okay. Okay, so that's that lemma. Okay, so second lemma is following that if you have a line segment, for any line segment, gamma contained in omega excluding k, there exists a sequence f sub n of rational functions such that one, f sub n converges uniformly to this term on K. right? So we're right, we expressed our function as a sum as a combination of terms of this form, and we're gonna find rational functions that approximate each of those terms. Okay. Okay. So we're gonna find rational functions that approximate these guys, and further, these guys have singularities only on gamma. Okay, so that's only, that is to say, outside of K. Okay, and the proof is basically to use the Riemann sum trick that we did before. So you say, well, suppose we have a parametrization of gamma of the curve gamma. This is bad notation, but so gamma is the curve. Gamma is also the parametrization of the curve. Then for Z and K, well, by definition, when we evaluate this, well, that's going to be the integral from 0 to 1 of f of gamma t over gamma t minus z gamma prime t dt. Right? Okay, so that's just the definition, and we'll call this thing f of z comma t. Okay. So now, right, so here's our curve, I'm sorry, here's our compact set, here's omega, and gamma is, some segment out here. Okay. Gamma is some segment out here, right, from the squares. Right, so notice that the distance from gamma to k is greater than some constant value. Okay. So there's some minimum distance between gamma because they're both compact. Okay. So that gives you that. Again, we get that. F is uniformly continuous on k cross 0, 1. The same, basically the same argument as before. So again, right, we get, so just as before, we let f and z be, these averages, f, c, k over n, k from 1 to n, right, which are, which look like k from 1 to n, f, gamma k over n, gamma k over n minus z, gamma prime k over n. Right? So we get these guys. Right? These guys as functions of z, these are rational functions in z. Right? Rational functions. Right? Rational functions with simple poles. Right, where their singularities are just of the form, 1 over z minus something. Right, right. Right. So these rational functions, have poles that that lie along, that are at gamma 1 over n, gamma 2 over n, gamma n over n. Right. So we've got these pretty simple rational functions that just have simple poles at those points. Okay. So, and then just as before, I get a uniform continuity implies uniform convergence. Okay, and so that gives it to us, right? We end up. Remember what we wanted. We wanted rational functions that converge to this function that had singularities only on gamma, and that's what we've got. It's okay. You guys don't look happy. Are you at least all right? Everybody all right? Any questions? Any questions? So we basically just made the rational functions, right? They are, here they are. Okay, so, now part 1 of Runge's theorem is done, right? Remember what Runge's theorem said, that that we could create rational functions that uniformly converge to our function, on K, which is what we've done, and that had singularities that were outside of K, right? And that's what we've gotten, right? Lemma number 1 gave us an expression for R in terms of integrals like these, and sums of integrals like these. And each of these guys can be in turn expressed as rational functions with singularities outside of K. So part 1 is done. Okay. So the only thing we have left to do is to show part 2. That is that if K complement is connected, then we can actually approximate using polynomials rather than rational functions. And so what we're going to do is we're going to take these rational functions. We're going to take this rational function approximation and then get polynomials that uniformly converge to these guys. Okay. So all that's left to prove part 2 of Runge's theorem. It suffices to show that following lemma, that if K complement is connected and you have some point in K complement, then this thing can be uniformly approximated in K by polynomials. Right? Because all of these rational functions that we created are things of this form, right? 1 over z minus some point that's outside of K. Yeah.
Oh, just like because gamma is
Outside of K, yeah.
Got it.
Right. So these points here, the singularities are all outside of K. So all we need to do is do with these guys. So. Okay. So here's the trick. Okay, so let's suppose that this is our set K, and let's suppose that this is our Z naught outside here. Okay. So let's suppose that this is the origin. We take a circle, a disk that's big enough to contain K. Okay, and choose a Z1 that's outside of it. So, okay. So, so in other words, choose a disk D centered at the origin that contains K, and choose any point Z1 that's outside of the disk. Okay. Then so this is kind of a strange thing to do, but we'll see why we get it in a second. So then notice that if we look at 1 over Z minus Z1, then we can rewrite that as negative 1 over Z1 times 1 over 1 minus Z minus Z1. Okay. So just algebra. We do some algebra, and then again we play the trick of the geometric series. Right? So this is summation negative Z to the n over Z1 to the n plus 1. So we just use the we use this trick, and notice that this which converges uniformly for Z and K. Right? By wire-stress M-test, as usual. Okay. So what's the point? The point is that the partial sums are polynomials. So we have polynomials that converge uniformly to 1 over Z minus Z1. That's not what we wanted, right? We wanted polynomials that converge uniformly to this guy. But what we have is polynomials that converge uniformly to this guy. But that'll be good. That'll be good enough. Okay. So okay. Okay, so I should say something a little bit more. So we have polynomials that converge to this guy, and thus we also have polynomials that converge uniformly to things of this, to powers of it. Okay. Because if we've got polynomials that converge to this, we just take powers of them, and we can get polynomials that converge to that. So, it suffices now. It suffices to show that 1 over Z minus Z naught can be approximated uniformly in K by polynomials in 1 over Z minus Z1. Wait, sorry, this should be a 1. Okay. Okay, so now we do something cool. We say, okay, I erased the picture. So take a path, right? We know that K complement is connected. So take a path gamma. Take the path gamma right, inside of the complement that goes from Z0 to Z1. Okay. So gamma 0 is Z0, gamma 1 is Z1. And let rho denote 1/2 of the distance from gamma to K. Right, so take the minimum distance and take half of that, and that's rho. Okay. So now this is kind of similar to something we did last time. Choose points omega 1 through omega L such that omega 1 is Z0, omega L is Z1, and the distance between them, the distance between successive points is smaller than rho. Okay, so we take all these points that are within rho of each other on the path. So we look at rho, right? We're still more than half the distance away from K. Okay, so and here's the key point that if W is a point on gamma and W prime is within rho of that point, then 1 over Z minus W, 1 over Z minus, 1 over Z minus W can be approximated by approximated uniformly on K by polynomials in 1 over Z minus W prime. Okay, so this is the cool thing, right? We were trying to show that, right? We wanted to show that we wanted to show that that this function could be, remember, we wanted to show that this function could be approximated uniformly in K by polynomials in 1 over Z minus Z1, right? And so, right, so, and we already got that we could approximate things out here, right? Hold on a second. Let me not get confused. Right. We had that things of this form could be approximated by polynomials uniformly out here, right? And so what we're doing is we're saying that we can shift that pole over, right? And say that we can anything of this form can be approximated uniformly by polynomials in in 1 over z minus the next guy, right? And so we can keep on going and push our way all the way back to z naught. And so these guys can be approximated by, if we go all through everything, we can get that these guys can be approximated by polynomials in 1 over z minus z1. Okay. And those guys in turn can be approximated by polynomials. So that would give it to us. Okay. Okay. So, right. Does that make sense? That make sense? Yeah, Kai.
Oh, okay, so I think I understand the idea is like you can approximate the next w with polynomials of the form like 1 over z minus the last w.
Yes, exactly. Yeah.
I'm maybe missing why do we know that based on rho?
Yeah, let me, I actually haven't proven it yet.
Oh, okay.
So-
Oh, I understand. You gave the proof sketch.
Yeah, I'm
I
just
got it.
sketching. Once we get this, then we'll be done.
Gotcha.
Okay, so yeah, so how does that happen? Okay, so proof. Right, so proof. Okay, so what's the point? Right, 1 over z minus w. It's kind of a similar trick to what we played before. We rewrite this in terms of 1 over z minus w prime. So we have 1 over z minus w prime over 1 times 1 over 1 minus w prime over z minus w prime. Okay, and then we play the same. We play the same geometric series trick. We get summation w minus w prime to the n over z minus w prime to the n plus 1. Okay, which converges uniformly for z and k. Right, and here's where the rho comes in, right? Because the distance between w and w prime is less than rho, right? W minus w prime, the distance is less than rho. The distance from z, well, z is in k. The distance from z to w prime is going to be bigger than rho, right? And so we're going to have this. We're going to have the Weierstrass M test again. So we get by Weierstrass M test. We get the uniform convergence. Okay. So then again, we use again approximation by partial sums. Finishes it. Right. We wanted to show that that 1 over z minus w can be approximated uniformly by polynomials in this. Well, that's exactly what we have here. We've got polynomials in 1 over z minus w prime. Right. The partial sums here are polynomials in 1 over z minus w prime. Right. So that gives us that, and then we can bootstrap our way all the way back. Okay. I hope that's all right. Yes, Noah.
Why do we have the 1/2 in the definition of rho?
Because in order to ensure, so that's this point right here, right?
Right.
So right, w minus w prime is smaller than rho. Z is in k, right? The distance from z to w prime. So if this is w prime is in the circle of radius rho.
Right.
Right. So then the distance from z to w prime has to be greater than rho. Right. That allows us to get that this is smaller than 1. And so we've got a geometric series that gives us, right, that gives us this term so that when we look at the wire stress M test, we get a convergent series.
So could we have also like chosen like rho equals 2/3 times the distance from gamma to k or something like that? It just has to be like less than the distance from gamma to k?
No, it would have to be less than half, 1/3 maybe, but not 2/3.
Okay.
Yeah. Right, because you want this distance, the distance from z to w prime, to be strictly greater than the distance from w prime to w. Right? If you allow 2/3, well, the distance from w to w prime could be greater than the distance from w prime to z. Here's the picture. Maybe the picture's not there. Here's w. Right. Here's rho. Rho is half the distance. Rho is half the distance to k. Right. Suppose z is here. Right. I think unless I misheard you, I think you said could you take 2/3 the distance?
Yeah.
Right. If you did that, then your w prime would be here, and your distance from w prime to w could be bigger than your distance from w prime to z, and that's a problem because you won't be able to use wire stress M test. Right. To use the wire stress M test, we need a geometric series that converges, right? But we would get like the sum of 2 to the n or something like that.
I'm not sure I entirely follow, but I can ask you about this.
Okay,
later.
we can talk right after. But yeah. Okay, that's it for today.
Thank you.
You're welcome. So read Schwartz reflection by yourselves. I was good.